because it is science time. We're talking today about gravity and friction. Maybe take extra good notes for if your homie is gone today. Gravity plus friction. Both of these two things, it should be pointed out, both of these two things are what kind of phenomena in the universe? They're both types of... Okay, yeah, we do describe them by talking about things like the laws of nature. We do talk about the law of gravity, but they're both... Forces. They are. They're both forces. These are both forces, and we talked about forces last time. And so this, for the third time this school year even, I am writing the word forces as basic. I'm going to try to throw this there, Miss Parr. If I don't get it, at least don't get hit by it, okay? Balla! There we go. Nice. Unfortunately, now we're going to have to switch to brown because I don't have any more blacks out. So these are both forces, which you remember, redefine forces for me. What's a force in general in the way we talk about science and physics? A force in general is a push or pull. Yeah, things that cause a change in motion. Remember? Things that cause a change in motion. And as the last little bit of our review, what do we call a change in motion? There's one word that means change in motion. Do you remember what it is? Acceleration. Good. So these are those phenomena in nature that cause an acceleration. That's what a force is. And two of the specific ones we're going to talk about are gravity and friction. The objective today is to diagram cause and effect in gravitation and friction. So we're going to write that down. Really good erasing. I'm going to have to try again with this stuff. Whoa, look at that. It's like a miracle. What was I going to do? Writing something. Diagram. We want to be really careful that the verb and the objective is actually being met. Diagram cause and effect. Also, one of these things is not like the other. Cause and effect in gravitation. Is it just in gravitation? And friction, yep. But in is the right word. In is the right preposition there. Not a big fan of that being brown and everything else being black, but that's okay. Diagram cause and effect in gravitation and friction. We're not quite there yet. We haven't diagrammed it yet. But what, in general, because of something we've already written on the board, what is the effect, or what can the effect be if either gravitation or friction is unbalanced? What could the effect be? A change in motion, which we abbreviate in science as acceleration. Good. So the effect of these, and as I say, if they're unbalanced, as with all forces, is a change in motion, an acceleration. But what causes them? That's another whole, well, that's kind of the point of what we're talking about. What causes gravity and what causes friction? Do you know? What causes gravity in general? Objects which have a fundamental property of the universe exert gravity on one another. What is that fundamental property of the universe? Objects which have what? What does something have to exert gravity on another object? Close, not exactly, and we'll talk about why in a second. Avery said weight, which is not exactly right. What do you think, Isaiah? Mass. And here on Earth's surface, which is where, for all of us, 100% of our experience lies, those two things are, if not equivalent, then they're at least measured the same. If I want to measure my weight in pounds, what tool do I use to do that? A scale. If I want to measure my mass in kilograms, what tool do I use to do that? A scale. Yeah, because here on Earth's surface, we equate those. Something that has more mass also has more weight, but they are not physically the same. Weight, have you ever seen this symbol before? Yeah, does not equal mass. Weight and mass are not the same thing in physics. And that's especially tricky for us as residents of Earth's surface, because on Earth's surface, not only are they effectively the same, but we measure them the same way, we treat them the same. And so this is kind of a hard thing for people to get across. But weight and mass are not the same thing. So let's, as part of teasing them apart, let's define them. So if weight is not mass, what is it? And if mass is not weight, what is it? Well, mass, trying to say this without making your mom a joke. What has more mass, a rabbit or your mom? The rabbit. Your mom. Why? Why does your mom have more mass? Why? Because she's a human being. That's good. That's good about your mom. She has more what? In what physics thing does she have more of than the rabbit does? Matter. Yeah, okay, good. I'm glad you said that instead of, they use a lot of stuff. Like your mom has a lot of stuff than the rabbit does, but more matter. So more mass is more matter. The bigger amount of matter something has, the bigger the mass is. Mass is a measure of how much matter an object has. Mass is a measure. Let's try to spell measure right. Measure of how much matter is in an object. More mass, more matter. What, by the way, do we use in the SI to measure mass?
Scale.
Good. That is what I was looking for. You're wrong. But what unit is what I was looking for?
Grams.
Yeah, but mostly kilograms. Grams are pretty small, so we usually use kilograms, but you're right. I can see how the question I asked was ambiguous. I asked, how do we measure mass? I meant, what unit do we measure mass in, which is kilograms, but we do, on our surface, as we said, use a scale to measure mass. In fact, it's actually very, very difficult to measure mass without just measuring weight. But we'll see why that's not actually a huge problem in a second. So mass and matter, or mass is a measure of matter. Just like you might say height is a measure of tallness, right? Mass is a measure of matter. If height is a measure of how much stuff you have vertically, mass is a measure of how much stuff you have in general. But then what is weight? They're not the same. We already know that. Weight is not the same as mass. Yes, the force of gravity acting on an object. So, I ran out of room. Hopefully, I'm going to try again. Acting on an object. Still kind of ran out of room. So, whereas mass depends on what and only what? How much matter it has. Weight depends on how much matter it has, sure, because it does depend on the weight, on the mass, but it also depends on how much gravity, the gravitational field in which it's in. So the example in your book is you've got, if you've already done your explorations, which I really hope you have, they were supposed to be due today, you've got a little robot. This is what he looks like. That's so cute. And he has a mass of, I think in your book it's 50 kilograms, but let's say it's 10 kilograms is how much matter is in him. That's a measure of his mass. M equals 10 kilograms. The robot at 2 different times is on the moon. This is the moon. I've drawn him in a different way. And the Earth. Try to draw him the same way there. Has his amount of matter changed, despite the fact that I drew him differently, just completely differently? Has the amount of matter in him changed? No. No, it's the same robot, so the same amount of matter. If this was you, like maybe depending on what you had for lunch or what's going on in your life, you might have lost some matter. But we'll say in this case that he has not. He has the same mass, 10 kilograms in both places. Why? First of all, is his weight different in these two cases? Yes, his weight is different. The robot's weight is different. Where does he have more weight?
Can you even measure weight in like that?
On the moon? Yeah, you can. So remember, this is how we draw forces. Which direction should I draw the force of gravity acting on an object? Down. His local down is towards what? Is it the same as my down?
Yes.
No, it's towards the center of planet Earth, right? So for us, that's how we define down, is the direction towards the center of planet Earth. And with that arrow, remember the length of the arrow is how strong the force is. Is that arrow going to be the same length or bigger or smaller on the moon? Smaller, because he has less mass? No. Because there's less gravity. That's what you said. Because the force of gravity is less. Why though? It's just a miracle. It's just the moon was unlucky in the gravity department. No. Why? Exactly. The moon itself has less mass. Little baby M. The moon has less mass than the Earth, which has great big mass. Like your mom. Depending on not only the mass, now we've got several things here. Not only the mass of the robot, but what else impacts the weight of the robot? Gravity. So does his mass impact his weight? Yeah. A bigger robot, big back robot, might have a mass of 100 kilograms. And in both of these places, he would weigh more also than the little robot, right? Just like I weigh more than you, all of you, put together, because I have more matter. I matter more. This robot also has more mass and weighs more than the little robot, because it has more matter. So what determines the force of weight? So F sub G, which F with a little baby g next to it, or weight, we use those kind of interchangeably in physics, equals what? What does it depend on? The influence of gravity, right? We abbreviate that lowercase g, the acceleration due to gravity, which actually I have written for physical science on the board right there above Trey's head. On Earth's surface, lowercase g is 9.8 meters per second squared. What else does it depend on? Yeah, that object's mass. So in both cases, it's the mass of the object times the acceleration due to gravity. And on Earth, g is 9.8 meters per second squared. And on the moon, g, well, actually we probably would call it a on the moon, but a is about 1.6. You'd have to actually look it up to be certain. I could be wrong, and that's not the point of this, but I think it's about 1.6. It might be 1.3. In fact, because I'm not sure, I'm just going to put a little squiggle over it. There, approximately 1.6 meters per second squared. So what is the cause? One of our objective was diagram the cause and effect of gravity. What is the cause of gravity? In one word. What physical phenomenon causes gravity? It is a force. Try again, though. What one single physical property of substances, of objects, gives it gravity? Mass. Every object with mass exerts gravity on every other object. That's the law of universal gravitation. The law of universal. Where? In the whole universe. The law of universal gravitation is the force of gravity between any two objects is equal to the gravitational constant times both of their masses factored divided by the distance between them squared. So it depends on the mass of the two objects. It depends on the distance between them. And this is the same for our whole universe, this capital G here. You don't necessarily need to know this math, but you do need to know what the force of gravity acting between two objects depends on. Any objects with mass, though, do these two markers exert gravity on each other? Yeah, some people are saying yes and some people are saying no. Physics tells us the truth is that they do. These do exert gravity on each other. Why don't we notice it?
Because it's balanced.
No. Good guess, but that's not right. Because they are, nope, gravity's a non-contact force. Good guess, but that's not right. Because they are, let me ask a question a different way. What do we notice the force of gravity? When it falls, right? When it's attracted to the Earth, because Earth is so
Magnetic.
not magnetic, because it's so, don't say fat, it has so much mass. So why don't we notice the force of gravity between these two objects? Because they have relatively little mass. If we did this with each of these weighing whatever they do, 100 grams, and the distance between them, even if they're only 30 centimeters apart, multiplied by this number, would give us a tiny, tiny, almost infinitesimally, almost invisibly small force. And the fact that they're in Earth's gravity too means that if I let them go, I'm not just holding them apart from each other. What else am I? If I let them go, what's going to happen? Yeah, you're right. You are a really good scientist after all. They fall because there's a much more massive object around that will attract them, which is the Earth. Does gravity cause acceleration?
Yes.
Always? Is this object accelerating? In this frame of reference, it's not. Why? Yeah, it's being held up by the hand. What do we call that force that my hand is providing here? The normal force. If I remove the normal force, it does accelerate. What if I remove the normal force? It does accelerate. It does change its motion. Its motion was stopped in this frame of reference. And if I remove the normal force, it changes to be downward. And you notice, if I drop it from higher, if I drop it from this high, you may not notice, but if I were to drop it from the building, you would notice that it not only moves down, but it gets faster and faster and faster as it goes down, right? Because its motion is changing, it's accelerating. That's the force of gravity on an object. What do we call the force of gravity on an object? No. Weight. Weight is the force of gravity on an object. What does the force of gravity depend on? Mass. The masses of the object and the distance between them. The further apart they are, gravity gets weaker. That's exactly right. That's why d squared is on the bottom of this equation. So what is this friction that someone has been telling me all about? What is friction then? So we said that gravity is exerted by all objects that have mass everywhere in the universe. What about friction? Okay. Yeah, rubbing. I mean, really, actually, the word friction, I believe, comes from the Latin for rubbing. But friction now is two objects. I shouldn't say two. Let's just put objects. What has to be true of things for friction, though? They have to, unlike gravity and unlike magnetism, they have to be what? Touching. We say the book calls that what kind of force? Contact force. Objects, let's put that. That sounds more scientific. Objects in contact, rubbing, and preventing. What does friction act to prevent? Yeah, motion. Exactly right. Objects in contact, rubbing and preventing motion. So, crazy example, kind of, but if I lift this up, will my cup fall off?
Let's find out.
Let's find out. It didn't. That's a really good demonstration. Why didn't it though? There is. Yeah. So we have. Let's. Yeah. Okay. Well, we'll get there in a second. Teague. Let's draw the forces on it. What force is acting on this cup? Gravity down. F sub g. What's acting up?
Normal force.
Normal force. Now, unlike gravity, which is always down, which direction is gravity always? Down. The normal force actually acts perpendicular to the surface. So when it's flat, or when it's perpendicular to the surface, it acts directly opposing gravity. But when it's not, the normal force, but look, there's something else missing. Something has to be acting on it in this direction. What do we call that? Force of what? Friction. That's friction. They're touching, and it's preventing motion. What if I really wanted this cup to fall down? What are some things I could do to reduce the friction?
Pick it up.
I could lift it higher, right? So the force of gravity, while still acting down, is less counteracted by the normal force. The normal force the normal force changes when I change the angle of the seat. And so, what else could I do to reduce the friction if I wanted this to fall down? Yeah, some kind of. She says WD-40. Other brands are available. Soap, oil, what? What are those things all together? You don't want to say it. You don't like to say this word, but what are all those things that reduce friction? Your book told you. What are they? Say it, Trey.
Lubricant.
They're lubricants, right, exactly. Lubricants reduce friction. Lubricant reduces friction. Why? Well, let's talk about what friction is in the first place. On the microscopic level, even though this feels smooth, nice and smooth, and this feels pretty smooth, on the microscopic level, those are actually like bumpity, right? Bumpity. And these little bumps, when it's sitting there, get kind of like nestled into each other. Once it starts to move, they kind of, they can move more and more because they're outside of the groove, right? But if they sit, they get kind of, what a term we use in physics sometimes is micro-weld. They chemically bond to each other on the surface. Which gets me to another way that we could increase friction. If we wanted to make it so that no matter what angle I lifted this at, it would definitely stay, what could we do to increase the friction? We could tape it. Use some kind of tape, glue, some kind of adhesive, which actually works to bond them together, chemically bond them together to make the micro-weld stronger, because that's what friction is. But if we wanted to, back to our reducing friction, if I put a lubricant in here, it fills in these little gaps, and so now, instead of being locked together like that, they're filled in with lubricant, and so they slide on each other. A lubricant reduces friction. So, another question, do only solid objects, what kind of question is this? Of course the answer is going to be no. Do only solid objects have friction? No, of course not. Give me some examples of non-solid friction. Air resistance. What's another one? Water resistance, yeah. So, Chana, would you get me, or someone, would you get me 2 Kleenexes, please? And I want my ball back. Trey, give me my ball back. So here's our demo for a combination of gravity and friction. Detention, Trey. No. I don't remember if I showed you this demonstration before, but I usually preface it by saying things like only idiots think this, so just don't be offended if I say that. What object is going to fall faster, a heavy object or a light object? Okay, only idiots think that. Let's write this down. You don't have to put the word idiot, but heavy objects don't, I'm going to put in tiny letters, necessarily fall faster. We're going to disprove this notion in 2 ways. Heavy objects don't necessarily fall faster. The weight of an object has nothing to do with how fast it falls. Not nothing, but that's not the main thing. Heavy objects don't necessarily fall faster. In fact, without air resistance, all objects on Earth fall at 9.8 meters per second squared. All of them. If there's no air resistance, all objects fall at 9.8 meters per second squared. Think about it this way. I gotta get some bigger objects. Give me a big object. Can I use your backpack, Alana? The answer is yes, I can. I'm not going to drop it. I'm just going to hold it for now, and then I'll ask you if I'm going to drop it. This is heavier than this. I can feel it in my arms. This is heavier. It's not like it's super heavy, but this is heavier than this. Which one has a greater force of gravity acting on it? What do we call force of gravity? Weight. Which one has a greater weight? The backpack. Which one has a greater mass? The backpack. So, in the case of, if we use our equation F equals ma, the backpack has a great big F, right? And a great big mass. And if we divide the mass over, we end up with some letter A. F equals ma, remember? Just some regular sized A. But the little ball has a small force of gravity, but also a small mass. So if we put numbers in here, we would, I'm supposed to try to draw those the same size. We would see, so let's say force 100, mass 100. 100 divided by 100 is 1. Force 1, mass 1. 1 divided by 1 is 1. They have the same acceleration of gravity, right? So the objects, and I'm not going to drop Alana's backpack, but if I drop that backpack and the little ball, they would fall without air resistance at the same rate. Let me show you. What falls faster, an idiot says? Heavy objects fall faster, right? So which one, if that's true, if heavy objects fall faster, which one of these are 2 Kleenexes, is going to fall faster? If an idiot is right, and heavier objects fall faster, which one's going to fall faster? No, I don't have the ball, I have 2 objects here. Yeah, if the only thing that matters is heavy objects fall faster, these should fall at the same rate, shouldn't they? Because they have the same mass. You're watching me with rapt attention as if you don't know what's going to happen. What's going to happen, obviously? Ready? We're getting there, because that's a smart people thing to say. But we're still acting like idiots. So to the idiot, heavy objects fall faster. Which one's going to fall faster? The same, right? Because, but that didn't happen. Now check this out. Now we have a heavier ball and a little tissue paper. Which one's going to fall faster?
They're equal.
In reality, they're equal, but the idiot says the heavier one, right? But they're the same. They're the same. Because it doesn't actually matter how heavy it is. It's air resistance. This one, these have the same mass, but this one has more, this one offers more air resistance. Like a parachute, like a feather. So does a feather or a brick fall faster? A brick, because the brick's heavier?
No.
Nope, because the feather has greater air resistance per weight, divided by its weight. The feather might not even touch the ground if it's windy. Could you imagine, have you ever played with that big parachute when you were in elementary school at PE? Do you think that weighs, in general, like when you get it out of its package, does that weigh more or less than a brick?
More.
Probably more. But if it was all spread out, do you think that would fall faster than a brick?
No.
Probably not. In fact, definitely not, because that's the point of a parachute. That would be a terrible parachute. So together, gravity and friction answer the question for us, why does it seem like some objects fall faster than others? In fact, in reality, some objects do fall faster than others, but it's because of air resistance, which is a kind of friction. Do you have questions about gravity and friction? I have a mess to clean up. Bye. Who's actually going to watch this, do you think? Yeah, who though?